You ever stop and wonder why some things just work? I mean, how can a jumbo jet fly for thousands of hours without a problem? Or how does the power grid somehow stay on during a massive storm? Well, I can tell you it is definitely not luck. It is all by design. And today, we're going to pull back the curtain on the hidden science of making things that last.
Look, we've all been there, right? Your phone suddenly freezes up. Your car decides it just doesn't want to start. The website crashes the second you're about to click buy. It's one of the most universal and infuriating frustrations of modern life.
So why does it happen? I mean, really, why do even the most brilliantly engineered pieces of tech eventually give up on us? The answer, it turns out, is both incredibly simple and amazingly complex. Just think about it for a second. A modern piece of technology isn't just one thing. It's this huge, sprawling web of interconnected parts. Your phone, your car, each one has thousands of components. And every single wire, every tiny little chip, is a potential point of failure. Honestly, when you think about it like that, it's kind of amazing they work at all, because the more complex the system, the more ways it can break. But what if we didn't have to just sit around and wait for things to break? What if we could actually build a kind of blueprint of a system, analyze its weaknesses, and literally design failure out from the very beginning? Well, that's the whole promise of reliability engineering. To do this, engineers use this incredibly powerful tool. It's a visual way of mapping out every single potential failure and understanding exactly how it could impact the whole system. And it's called a reliability block diagram. And here we go. This is our main example for today, a reliability block diagram for a quadcopter drone. I know, at first glance, it just looks like a bunch of boxes and lines. But this is the blueprint for reliability. We're going to break this down piece by piece. And I promise, by the end, you'll see exactly how this chart helps prevent this drone from just falling out of the sky. So what is an RBD, really? At its heart, it's a logical map. It shows you all the parts of a system, and this is the crucial part, how they're all connected in terms of what they do. It lets an engineer ask a very simple question. If this one part right here fails, does the whole system go down? So how do we use this map to actually make the drone more reliable? Well, the single most important strategy is something called redundancy, which is really just a fancy way of saying you need to build in backups. Let's look at the different ways engineers can do just that. Okay, the most basic setup is called a series configuration. You can think of it like those old school holiday lights, the ones where if one bulb goes out, the whole string dies. It's the same idea. On our drone's motherboard, the flight controller, the SEC, and the receiver are all in a series. If any one of them fails, the whole motherboard is dead in the water. It's a chain, and it's only as strong as its weakest link. Now, to make things stronger, we can use a parallel configuration. Take a look at the drone's 4 motors. They are all spinning at the same time, but, and here's the clever part, the system is designed so that it can stay in the air even if one motor fails. It only needs 3 out of the 4 to keep flying. That is a safety net built right into the design.
And then there's a third way, standby. So this drone has 2 batteries, but only one is actually being used at any given time. The second one is what we call a cold standby. It's totally off, just waiting in the wings. If that first battery fails, the system instantly switches over to the backup. It's exactly like having a backup generator for your house. It's there just in case disaster strikes.
Okay, so here's the key difference between those 2 ideas. In a parallel setup, like with the motors, all the backups are running at the same time. But in a standby setup, like with the batteries, the backup is completely dormant. It's asleep, waiting to be woken up only when it's absolutely needed. And that's fantastic for saving energy and reducing wear and tear on that spare part. Now, building in backups is a great start, but it's not the whole story. You see, in the real world, failure isn't just a simple on or off switch. It's a lot more nuanced than that. To really design a reliable system, engineers have to understand the specific language of failure. Yeah, not all failures are created equal. A brand new component might fail because of a tiny defect from the factory, while a much older one might just wear out from use. And some parts just fail at a completely random rate. What you're seeing here is a list of the statistical models engineers use to describe all these different behaviors. They don't have to guess. They can use data to create a kind of mathematical personality profile for every single part, predicting how it's likely to fail over its lifetime. And getting that data right is absolutely critical. This code explains why perfectly. A doctor may erroneously conclude a disease is common if they only see 6 patients. It's a brilliant analogy, right? If an engineer only studies the components that have already broken, they're going to get a totally warped picture of reality. To truly understand reliability, you have to look at the entire population of parts, the ones that are still working, just as much as the ones that have failed. So, you have this incredibly detailed map, and you understand the language of failure for each part. How do you use all that to find the system's Achilles heel? Well, this is where the analysis provides some incredibly clear, actionable insights. Engineers start looking for something called cut sets. A cut set is basically any combination of component failures that will bring the entire system crashing down. For our drone, the flight controller failing all by itself is a cut set of 1. But 2 of the motors failing is also a cut set. The goal is to identify every single one of these critical failure paths. And this is the whole point of the analysis. Find all the cut sets. They are, in effect, the system's blueprints for disaster. And once engineers have this list, they have a targeted hit list. They know exactly where to focus their efforts, either by adding more redundancy or just using a stronger component to literally cut that path to failure. All of this analysis spits out some incredibly useful numbers. One of the most important is something called MTBF, or mean time between failures. This tells you, on average, how long your entire system is expected to operate before something goes wrong. It's a single, powerful score for a system's overall reliability. And here it is. This is the ultimate payoff. All of that complex math gets boiled down into a simple, actionable dashboard just like this one. This top unreliability blocks chart, well, it's like a treasure map for the engineering team. It tells them, hey, don't waste your time on anything else. Start here. Fixing these specific parts will give you the biggest bang for your buck in improving the entire system's reliability. So, okay, we've been looking at a little drone. But this exact kind of thinking is absolutely crucial for the complex, high-stakes systems that all of us depend on every single day. I mean, just think about it. A commercial aircraft has a parallel design for its engines, so it can keep flying even if one of them fails. Hospitals use standby generators to keep life support machines running during a blockout. The entire power grid itself is a massive web of all these different configurations. The stuff isn't just theory. It's the invisible science that keeps our world from falling apart. And that right there is the crucial point. The fact that these incredibly complex systems work so well for so long, that is not an accident. It's not luck. It is the direct result of this methodical, predictive, and deliberate science. So the next time you board a flight or even just flip on a light switch, just take a moment. Think about the hidden blueprints, the complex calculations, and all the brilliant engineering that you can't see. And ask yourself, what other invisible systems are working perfectly right now just to keep your world running?